Good morning, everyone. Myself, S. Kokila, Assistant Professor in the Department of Chemical Engineering in Erode Sangathar Engineering College. Today, I am going to handle a GATE section on chemical process calculations on the title Mass and Energy Balances. My subject is Chemical Process Calculation. My title is Mass and Energy Balances. First, in this session, we will going to discuss about the specific heat, enthalpy, heat, sensible heat, latent heat, saturation temperature and pressure, saturated liquid and vapor. This is the outline of this session. Next, phase diagram of water, that is liquid and vapor phases, which includes subcooled liquid, condensate, steam. Steam, it is a mixture of condensate and vapor. Next, vapor and superheated steam. Next, steam table, steam quality, superheated steam, energy content, it is also known as enthalpy, which includes liquid products, steam. Next, mass and energy balances. Mass and energy balances of batch and continuous processes include mixing and heating. Next, direct and indirect contact heating. Next, indirect cooling, contact cooling, and determination of steam quality. First, specific heat. The unit of specific heat is joule per kilogram Kelvin. It is represented as Cp. It is the specific heat is defined as the energy required to raise the temperature of unit mass of a substance by unit value. It varies with temperature. However, for approximate calculation, Cp for water is assumed to be 4180 joule per kilogram Kelvin. Next, enthalpy. It is represented as H and its unit is joule per kilogram. It is defined as the heat content of a system. It is always expressed relative to a reference state, that is usually 0 degrees Celsius. Generally, enthalpy is assumed to be 0 at 0 degrees Celsius. For most liquids, enthalpy is similar to specific heat, that is temperature in degrees Celsius. Next, heat. It is represented in joules and the unit is joules and it is represented as Q. It is defined as the energy transferred due to temperature difference between the system and the surroundings. When energy transferred is represented by unit time, its unit are joule per second or watt. The energy transferred may be utilized as sensible heat or latent heat. Sensible heat, the energy transferred from hot or cold object. That is for batch system, Q is equal to mCp del T. The formula is Q is equal to mCp del T. This will be used for solving a problems in GATE examination. Here Q is in joules. Next, for continuous system, Q is equal to mCp del T. Here Q is in joule per second or watt because it is in a continuous system. Next, latent heat, it is represented in joules or joule per second. The energy, it is defined as the energy transfer during process change without any temperature change. For batch system, Q is equal to m lambda. Here Q is in joules and for continuous system Q is equal to m dot lambda. Q is in joule per second or watt. Next, latent heat of vaporization, that is represented as lambda vapor and its unit is joule per kg. It is defined as the energy required to convert 1 kilogram of a liquid to vapor phase without temperature change. It equals energy released when vapor condenses to liquid at the temperature. For heating foods, the energy of condensing steam is made use of. The latent heat of vaporization of water at 100 degrees Celsius is equal to 2257.06 kilojoule per kilogram. These values are used in solving problems and gate questions. Next, latent heat of fusion. It is represented as lambda fuse and its unit is joule per kilogram. It is defined as the energy required to convert 1 kilogram of a solid to liquid phase without temperature change. Latent heat of fusion of ice at 0 degrees Celsius is equal to 333.2 kilojoule per kilogram. Next, saturation temperature and pressure. Any substance can exist in more than one phase at one time. For any pressure, there is a temperature at which a liquid can coexist with the vapor phase. This pressure and the corresponding temperature are called the saturation pressure and the saturation temperature respectively. Example, water at 101.3 kilopascal, that is atmospheric pressure, has a saturation temperature of 100 degrees Celsius. At higher pressure, saturation temperature is higher. Next, saturated liquid and saturated vapor. When only liquid phase exists at the saturation temperature and pressure, the liquid is called a saturated liquid or condensate. Its enthalpy is denoted by Hc. When only vapor exists at the saturation pressure and temperature, the vapor is called saturated vapor. Its enthalpy is denoted by Hv. Next, phase diagram of water. The phase diagram of water is expressed for pressure versus enthalpy. Here, within the dome, water exists as a steam, which is a mixture of liquid and vapor. Here, temperature and pressure are constant, are called the saturation temperature and saturation pressure, respectively. The left side of the dome is known as the subcooled liquid. Within the dome, it is saturated steam, and right of the dome, it is superheated steam. In the subcooled liquid, there will be that point is known as a saturated liquid. In the right side, that is superheated steam, is known as saturated vapor. Within the dome, the temperature is maintained at constant. This is a saturated steam table. This will be useful in gate examinations. Here, what is the latent heat of vaporization of water at atmospheric pressure? Here, the formula is latent heat of vaporization at atmospheric pressure is equal to Hv at atmospheric pressure minus Hc at atmospheric pressure. That is enthalpy of vapor at atmospheric pressure minus enthalpy of condensate at atmospheric pressure, which is equal to 2676.1 minus 419.04, which is equal to 2257.06 kilojoule per kilogram. Here, these values are from this steam table. We have to find that at 361.3 degrees Celsius temperature, what is that saturated vapor value and liquid value. Next, steam quality. It is represented by X. The term steam generally refers to the saturated steam and not superheated steam. Steam is a mixture of liquid, that is condensate and vapor. The enthalpy of steam Hs is a weighted mean of enthalpy of condensate Hc and the enthalpy of vapor Hv. Hs is equal to x Hv plus 1 minus x into Hc. Here x represented is known as steam quality. On rearranging this, x equal to Hs minus Hc divided by Hv minus Hc. Here x equal to 0 when Hs equal to Hc. When the enthalpy of steam is equal to enthalpy of condensate, the steam quality X will be 0. When the enthalpy of steam is equal to the enthalpy of the vapor, that is Hs equal to Hv, the steam quality will be 1. Higher the steam quality, higher the value of Hx. This is given by 0 less than or equal to x less than or equal to 1 or 0% less than or equal to x less than or equal to 100%. Hc and Hv at saturation temperature and pressure are determined from steam tables. Next, superheated steam. When the temperature of vapor is greater than the saturation temperature, at its saturation pressure, the steam is referred to as superheated steam. The difference between the steam temperature and the saturation temperature is the degree of superheat. Superheated steam at a given pressure can have different temperatures greater than the saturation temperature, unlike saturated steam. Thus, to define a state of superheated steam, one has to specify the temperature and pressure. To determine the state of saturated steam, one has to specify either temperature or pressure. Next, Q versus T. It is a graph of Q, that is energy supplied, and the temperature in degrees Celsius. Here, S is a sensible section and L is a latent section. Here, the first line indicates the sensible line, and this line is a sensible to latent line, and this is sensible line. Here, latent to vapor, and next is vapor, that is sensible line. Here, Q1 is equal to lambda of fusion, that is ice, which is equal to 333.2 kilojoule per kilogram. Next, Q2 is equal to Cp, specific heat of water. So del T equal to 419.04 kilojoule per kilogram. Next, Q3 equal to lambda vapor of water, which is equal to 22,057.06 kilojoule per kilogram. Here S represents the solid, N represents the liquid, and V represents the vapor. And L plus V represent the saturated steam, V represented the superheated steam. Next, energy content. Thermal energy content of a solid or liquid can be determined by MCP. The MCP T. T is in Kelvin, means that is the value is 273, or MCP T, if it is in Celsius, means 0. This is based on the assumption that the energy content of the substance is 0 at 0 degrees Celsius, that is equal to 273 Kelvin. Thermal energy content or enthalpy of a steam is given by MS/Hs. Note Hs equal to XHV plus 1 minus X into Hc. Here Xv is an enthalpy of vapor and Hc is an enthalpy of condensate, and Hs is an enthalpy of steam. Next, heat exchanger. It is represented at Hx. An equipment where heat is exchanged between two products is known as heat exchanger. Steam losing heat and cold product gaining heat. Hot water losing heat and cold product gaining heat. Cold water gaining heat and hot product losing heat. They may be batch or continuous and indirect or direct or indirect contact. Batch heating, home microwave oven is an example. Next, continuous heating, pumping a product through a tube and heating it by steam or hot water from outside. Direct contact heat exchanger, batch heating and continuous heating. Batch heating, mixing steam with milk in the making of cappuccino. Next, continuous heating, steam injection or infusion for a flowing product. Next, indirect contact heat exchanger. This also includes batch heating and continuous heating. Retorts for canning double tube, plate, shell and tube. These are some examples of heat exchangers. Next, direct and indirect contact heat exchanger. Direct contact heat exchanger. Steam contacts product and mixes with it. Steam loses energy as it condensates. Product gains energy. Rapid heat transfer, however, product is diluted. Vacuum may be used to remove added water. Next, indirect contact heat exchanger. The example for indirect contact heat exchanger is concentric metal pipes. Steam is separated from product by a barrier, which is a metal pipe, not as much as or as rapid heating. However, product is not diluted. Energy transferred by steam to a product in a direct contact heat exchanger is given by Ms into Hs. Energy transferred by steam, where when steam condenses completely to a product in an indirect contact heat exchanger is given by Ms into Hs minus Hc. Next, mass balance. Overall mass balance. For any system, the total mass going into the system must be equal to the total mass coming out of the system plus any accumulation of the mass in the system. This is given by input is equal to output plus accumulation. Batch system means mass will be in kg, and if it is a continuous system, mass flow rate will be in kg per second. Next, component mass balance. For any component in a system, the total mass of that component going into the system must be equal to the total mass of the component coming out of the system plus any accumulation of the component in the system. This is given by input of the system, which is equal to output of the system plus accumulation of the component within the system. For any system or subsystem, the number of mass balance equations is equal to number of components in the product. One mass balance equation can be written for each component. Next, energy balance. For any system, the energy going into the system must be equal to the energy coming out of the system plus any accumulation of the energy in the system. Only one energy balance equation is written for any system, irrespective of the number of components in the products. Once mass and energy balance equations are written, make sure that the number of equations and the unknown numbers are in equal. Next, application of mass and energy balance. Mixing or separation of streams of products with different composition. Condensation of steam outside a tube through which product flows. This is known as indirect contact heating. Next, mixing of steam with the product. Direct contact heating. Direct contact heating is faster than indirect contact heating. Side effect of direct contact heating is dilution of product. Vacuum may be used to evaporate water that was added. Next, evaporation of water from a product to concentrate it. For batch systems, the term mass is used, and for the continuous system, the term mass flow rate, that is m dot, is used. Here, the mass will be in kg and the mass flow rate will be in kilogram per second. Next, mixing of two products in a batch system at the same temperature. Here, a mixer is given. In this, M1 and X1 will be the total mass and the mole fraction of a solid. M1 is the total mass and X1 is the solid fractions at the input stage, and M2 is the total masses of a substance 2, and X2 is the total mole fraction of a substance 2. Next, M3 is the total output of the mass M3, and X3 is the mole fraction of the solids at output. The overall mass balance equation is given by output input is equal to output. Here we have an input of M1 and M2 and our output is M3. So M1 plus M2 is equal to M3. The total solid balance equation is given by M1 into X1, that is the product of masses into the mole fraction. M1 into X1 plus M2 into X2, that is for product 2, which is equal, input 2, which is equal to the output M3 into X3. Next, we can write the equation at our total mole fraction will be equal to 1. So x1 will be equal to 1 minus x1, and x2 will be equal to 1 minus x2, and x3 will be 1 minus x3. That is for total water balance equation. The total water balance equation is, however, not a totally new equation. It can be obtained by subtracting the solid substance equation from the overall mass balance equation. Thus, there are only two equations for the above system. Hence, given any four variables in the system, the other two variables can be determined. Note that the six variables in the above system, M1, M2, M3, X1, X2, X3. Also note that in a system such that one shown above, X1 plus X2 not equal to X3, that is the mole fractions of the input will not be equal to the mole fractions of the output, but the total masses of the input will be equal to the total masses of the output. Next, mixing of two products in a batch system at different temperatures. Here, M1 will be the total masses of the input of substance 1, and X1 will be the solid fractions of the substance 1. Cp1 is the specific heat of the substance 1, and T1 is the temperature of the substance 1. Similar to that, M2 will be the total masses of the substance 2, X2 will be the solid fractions of the substance 2, Cp2 and T2 will be the specific heat and temperatures of the substance 2. Next, Cp3 will be the Cp3 and T3 will be the specific heat and temperature of the substance 3, and M3 and X3 will be the total masses of the substance 3 and mole fraction, or that is solid fractions of the substance 3, that is coming out from the mixer. The total mass balance equations are the same as before, but the energy balance equations, when temperatures are in Kelvin, means the energy balance equation can be written as mCp del T. So M1 Cp1 into temperature difference, that is T1 minus 273. Next, our input is substance 2. So M2 into Cp2 into T2 minus 273, which is equal to M3 into Cp3 into T3 minus 273, that is our output. When energy balance equation, when temperatures are in Celsius, we can write as simple as M1 into Cp1 into T1 plus M2 into Cp2 into T2 is equal to M3 into Cp3 into T3. Here, Cps is a specific heat of solids, and Cp3 will be written as x2 into Cps plus 1 minus x1 into Cpw. That is, we are subtracting the solid fractions to find the water specific heats. Next, direct heating of spin or continuous system. Here we have given with the direct contact heat exchanger. Here our input is cold product with mass flow rate and some amount of mole fraction XF and specific heat CEF and temperature of a feed. So M. Here we have given a steam. The flow rate is M dot S and the quality of steam is given as X and pressure is P and temperature is T. Our output will be the warm diluted product. The warm diluted product has a mass flow rate of Mp and Xp is the quality of the steam and Cpp is the specific heat of the product and Tp is the temperature of the product. Here Mp, X, Cp and T are the mass flow rate, solid fraction, specific heat and temperature respectively. Subscripts F for feed and P for the product. The overall material balance for the above system can be written as mass flow rate of the feed plus mass flow rate of the steam, which is equal to the mass flow rate of the product. Here F and feed and steam are our input and product is our output. Next, solid balance Mf into Xf is equal to Mp into Xp. Next, energy balance is Mf into Cpf into Tf plus Ms into Hs equal to Mp into Cpp into Tp. Next, Hs, that is steam enthalpy, which is equal to X into Hv plus 1 minus X into Hc. Here Hv and Hc are determined from the steam tables at the steam temperature and steam pressure. Determination of steam quality. Ms quality of X pressure or temperature is given. Here we have given with the flask. Here input will be our cold water with mass flow rate of Mc and specific heat Cpc and temperature Tc. And steam is our input and our product will be hot water. Here mH is the mass flow rate of hot water, Cph is the specific heat of hot water and Th is the temperature of a hot water. Here, similar to the above step, we can write the steam enthalpy, which is equal to X into Hv plus 1 minus X into Hc, with Hv and Hc being determined from the steam tables at the absolute steam temperature of P and steam temperature of T. X is equal to Hs minus Hc divided by Hme minus Hc. Next, indirect heating of the steam is continuous system. Mf, Xf, Cpf, Tf is the whole product input. Here F is a subscript of feed, M is a mass flow rate of feed, Xf is a mole fraction of the feed, Cpf is the specific heat of the feed and Tf is the temperature of the feed. Here we are given with an indirect contact of heat exchanger. So here steam is given as in the form of condensate. So temperature is T is converted to 100% condensate. Our product will be a warm undiluted product. Here Mp, that is mass flow rate of the product, Xp is the mole fraction of the product, Cpp is the specific heat of the product and Tp is the temperature of the product. The overall mass balance of the above system can be represented as M dot F is equal to M dot P. That is, input is equal to output. Mass flow rate of input, feed is equal to mass flow rate of the output, that is product. The solid balance is given by mass flow rate of the feed into mole fraction of the feed, which is equal to the mass flow rate of the product into mole fraction of the feed. Thus, Xp, which is equal to Xf. Here, therefore, if the total mass flow rate is equal, the mole fractions also will be equal. The energy balance equation can be written as mf into cpf into tf plus mp into hp. These are our hs, these are our inputs, and output will be mp into cpp into dp plus ms into hc. Here h is equal to x into hv plus 1 minus x into hc. Here both hv and hc being determined from the steam tables at absolute steam temperature of pressure and steam pressure of P and steam temperature of T. Next, indirect cooling with water as a continuous system. Here, our input is hot feed and our output is cold feed. Input has a mass flow rate of mf and mole fraction of xf and specific heat of cpf and temperature of f. And our product has a mass flow rate of mp and mole fraction of xp and specific heat of cpp into temperature of Tp. Here, the overall material balance is given by Mf is equal to Mp. Next, the solid balance is given by Mf into Xf is equal to Mp into Xp. Similar to the same above, if the mass flow rate are equal, then the mole fraction will also be equal. Energy balance equation is given by m dot f into cpf into tf plus m dot cw into cp1 into t1 is equal to m dot cw into cp2 into t2 plus m dot p into cpp into tp. Here CP1 and CP2 are determined from the tables containing the properties of water at temperatures T1 and T2 respectively. T1 and T2 respectively. When approximations are used, CP1 will be equal to CP2. Therefore, it will be equal to 4180 joule per kilogram Kelvin. That is specific heat of water. Next, the total summary. Here, from this energy of a liquid, that is M, energy of a liquid is equal to mCp T in Celsius. Then energy of a steam is equal to Ms into Hs. Steam saturated steam tables, enthalpy of condensate Hc and vapor Hv at various saturation temperature and pressure. Next, steam quality, the measure of the amount of steam in vapor from amount of steam in vapor form. It ranges from 0.0 to 1.0 or 0 percentage to 100 percentage. Next, calculations for direct heating using steam. Next, overall mass balance. Steam is a part of the overall mass balance equations. Next, energy balance equation. No need to factor the energy of steam on right hand side of the equations. Next, calculations for indirect heating using steam. Overall mass balance. Steam is not a part of the overall mass balance equation. Next is energy balance equation. Energy of steam as it exists, the steam has to be included on the right hand side of the equation. Thank you.